heat transfer and particularly conduction. And so the general equations you'll see are similar to ones you've seen before. So we know that Q is equal to, oh, someone's in the chat. I should get that set up. 1 second. Numerical methods, thank you. Okay, so we know the general equation for Q rate was equal to Ka over delta L T2 minus T1. And so this is the thing we're going to see a lot. And then we also have our conduction and radiation. And this is for, remember, there's all these simplifications that were associated with this equation. So steady state was one of them. No heat generation for this particular equation. So we'll see that for these numerical methods, we're going to split up heat generation and conduction and treat them kind of individually. And so the equations here are quite basic. And then we're just, a lot of it is just kind of learning how to treat each situation. So there's actually a pretty good spread in this set that will deal with hopefully as many of the situations that you're going to come across. So we're going to jump right to question 2. Question 1 and question 2 are pretty similar topic, and question 2 is a little bit more interesting. Okay. Still have not quite figured this out. Okay, so we have this wall, and this just is basically a wall with a bunch of different stuff going on, so that way we can test everything out. So we have a heat flux hitting this wall. We also have convection leaving up. We have radiation going on the other surface. Over here, there's no convection. And then what we've done is we've split this wall into 3 nodes, and we're going to describe it with these nodes. And basically, the more nodes you add, the more information you have if you're looking for more intermediate information. And it also increases the accuracy. And so this situation, or this picture down below, this is from the textbook. And I just think it's important just to see the way they're splitting it up. So you're dealing with a node, but you're essentially dealing with this space that's equal on either side of the node. And so that'll be important when we write some of the equations. And so your nodes are delta x apart. So the distance between m1 and m plus 1 are delta x, but then also this space is delta x. So you'll actually see delta x be used for different situations, and hopefully this picture will help you understand when we cut it by half and not. So we're considering one-dimensional heat conduction. That's important. Variable heat generation and variable thermal conductivity. So what this is saying is we just don't know. We don't know kind of the heat conduction can change, the conductivity can change, but the idea here is that we're dealing with discrete. So at each point, we're going to assume the same conductivity. So we want to create this nodal network with 3 nodes, uniform spacing, using the energy balance approach, obtain finite difference formulations for this problem. So essentially what we're doing is we're just going to create our 3 equations. So for this one, we'll have 3 equations, one for node 0, one for node 1, one for node 2. And then we're not actually going to go through and solve them because we're not given any numbers in this one. But anytime you have 3 equations and 3 unknowns, you are able to solve the problem. So for our, some extra trouble today. For our node 1, or sorry, our node 0, we'll start with. Okay, so the first thing we want to be interested in is the heat flux on this side. So we're going to say our heat flux, and we're going to say that not just because that's what we've called this node, times the area. So we know that the heat going into this is just heat flux. Then we're going to want to incorporate our conduction, and our conduction is H A T infinity minus T naught. And so just as far as direction, whether or not you do naught minus infinity or infinity minus naught, I find it helpful to just, you don't have to do it every time, but just at the beginning, you can draw an arrow of kind of like where you're assuming this heat flux to go. And then you just write the temperatures in the order of your arrow. And so the way this works is it actually doesn't matter because we're talking about this node. So if we're adding heat into this node, then it's going to be infinity minus 0. And then if we're removing heat from the node, it's going to be minus infinity minus 0. So if we're assuming this direction, we would subtract that energy. So hopefully as we go through a number of examples, that'll start to make a bit more sense. And then there's going to be some level of conduction coming in here. So we're going to add. And so again, that by adding, it means we're assuming heat is going in. And then we're going to take our conduction in this direction. So K naught A T1 minus T0 all divided by delta X. So this is the conduction equation we're used to. And this delta X refers to this delta X different distance. So this is what I mean by we're looking at delta X in two different ways. So we'll see on the next one how that plays out. So the last part of this was that there's variable heat generation. So this variable heat generation is, we're going to be adding it because we're generating it. We'd subtract it if it was being removed. And you'll notice that there's K naught and there's E naught. This is because we were told it's variable. So this is the heat generation at this node, and that could be different than the heat generation of this node and the heat generation of that node. All right, so this is going to be times area delta X over 2. Okay. And the reason why, it's delta X over 2 is because we're considering the heat generation in this kind of half on one side, half on the other side node. But of course, for this node, the half that's on this side of the node, the delta X over 2 on this side, isn't generating any heat because it's actually outside of our body. And then the half on this side is, so that's why we have X over 2. Hopefully that makes sense. I'll go to the next two a little bit more quickly. So for node 1, this is the one that's in the middle. We have our conduction from our 0 side. So for this particular one, we're talking about the one node. So we're looking at the K at that particular discrete point. So our K1 area, and then T naught minus T1 over delta X. So that delta X is the distance between 0 and 1. T2 minus T1 over that same delta X, this time it's between 1 and 2. And then we're going to add our energy generation. And then this time we're going to not divide delta X by 2. And we're not dividing delta X by 2 because this time the energy generation is happening on both sides of this node. So this is our delta x. Hopefully that makes sense. And then our last node, this time we have our radiation. We have our conduction. And then once again, we have our generation, and because this is also an edge node, we're going to be dividing that delta x by 2. And I've just realized that all of these are equal to 0. It's an important factor. And this is essentially saying we've accounted for everything entering and exiting the node, and so therefore the sum of all of them is going to be equal to 0. So now we would have 3 equations. We have 3 unknowns, which is all of our temperatures. And we'd be able to solve this problem, assuming we knew what the boundary conditions were. Any questions about that? No, forget, I am watching the chat. So if you want to ask there as well, that also works. So here's another one, and you've kind of seen now, I guess, how it all breaks down quite nicely. So even if it's something complicated like this, we have flex here, we have convection here and radiation, and then we have this change of surface and an interface. Even that, it's all just broken down into each node you just treat differently. And so the idea here is that because it's so simple and just fairly repetitive, a computer can solve it. That's the idea. So typically for a person solving a problem, you want kind of the cleverest tricks and the simplest way to solve it. And for a computer, you want something that's very repetitive and not very situational, specific. So let's just take a quick look. So we have a stainless steel plate attached to a copper silicon plate, and then we have just the information about the 2 plates by the standards, but just to avoid having to look those up, I summarized them here. And then what's the highest heat flux at the bottom of the surface? So what is the highest heat flux of the bottom surface can be subject to such that the plate is still operating below 93 degrees Celsius. So we're looking for this. And mostly I'll just focus on how to set up these nodes. So our node 0. So for this, we have our heat flux. Again, we have it going into the node, so it's positive. So area plus, and then we have the convection. And so there should have been area there. And so often in these kinds of questions, what they'll do is they'll just cancel with the area because all this is equal to 0. But you do need to be careful to make sure that that's allowed. In this case, it is. So that would be our...
Excuse me, sir.
Yep.
Do you divide the delta x to 2 for half for the 0 node?
That's a good question. So in this case, so in the last case, we were talking about generation, and generation happens within the solid. And so we would be looking at this delta x as our kind of interesting thing, or delta x over 2, and then there'd be a delta x over 2. But even in the last question for the conduction, So this conduction is talking about the distance between node 1 and node 0, which is also delta x. So in this case, we are dealing with just delta x.
Thank you.
Okay. All right. And then for node 1, we have our K1, so K1 being the K of our silicon plate, not the K of our node. So we're using a slightly different subscript here. So that's why it's K1 for both. And then this one, all we have on either side is conduction. So just the conduction on either side. And this is often simplified down. So this is something you've probably seen in your textbook. So you can see that as long as our material is the same between the two nodes, we can cancel those out. And as long as our spacing is uniform, we can cancel those out. And so we end up with T naught plus T, or actually it's often done in the other order. So T naught minus 2 T1 plus T2 is equal to 0. And so that's a nice way to simplify it down, but just keep in mind that you need a couple. It needs to be uniform K and uniform node distances. And so this will actually generalize. So this is going to be node 1 to 5. We're going to use this T, and just to generalize it, T minus 1 minus T M. T of M plus 0. And again, this is useful, even if it's not necessarily for you solving the equation, it would be useful for you to enter into a computer, because computers like repetitive things. Okay, and I know we've kind of lost the picture, but we'll just look at the interesting nodes from now on. So I'll go up for 1 second. Okay, so the next thing we're just going to look at 6 and 8 as the interesting things. So 6 is on the boundary, 8 is on the edge. Okay. So node 6. So for this one, we have conduction coming from either side and from either one, or from the top, the node above and the node below it, but those two different nodes are different temperatures, so we can't use the super generalized one. So we're going to do K1. We're still going to do the simplification where we cancel out the delta X. So this will be a little simplified. So that's the conduction from below. And then we have a different material. That's equal to 0. And then our node 8. We have our H, T infinity minus T8. So we have our convection. And then again, our conduction comes from comes from the delta x, it's the full distance. So just because it's on the edge, in this case, we still use delta x because we're talking about from the adjacent node. It's equal to 0. All right. So you can hear me stuttering a bit for a second. The answer key is, I guess, let's skip a couple steps. So you know that we have a surrounding temperature. Okay, I think just given time and because there's more to cover, we might have to move on. So just to clarify, in my answer key, it calls this H combined. So this is meant to include the convection and the radiation. And then this is 8 infinity. And so I guess the assumption there is that our T surroundings and our T infinity are the same temperature. We were going to do that. And we're making that simplification that you maybe saw during your project, where we can express radiation as though it's convection. This question isn't from your book. It seems to be from something else. And to me, it doesn't seem that complete. So I think I'm just going to leave it with the nodes set up for now. Yeah. Okay. So we'll move on. Question 4 and 5. So this we're actually going to get into two-dimensional. Heat transfer. And so this is another place where this kind of numerical methods. Okay, so Tim just asked, when do we refer to T ambient and T infinity versus T surface? So it's a good question. So T surface usually refers to this, and we sometimes just use this. So that's usually what we're talking about with T surface. And then T infinity, it's usually the same as T ambient. I haven't seen it a lot in this textbook that they call it ambient, but that is what they're referring to. So they're talking about the air temperature. And on a surface, the infinity specifically refers to the fact that if we have our surface temperature, then if we were to plot this temperature, let's say it was high and it was being cooled by the surroundings, it would kind of look like a shape like this. And so in this case, the solid is here, and all of this temperature profile is in the air. And so really close to a surface, the air itself will be heated up. And so we can't just call it T air temperature, because the T air temperature here is different than the T air temperature here. So the T infinity refers to far enough away from the object that it's no longer being affected. And then the fact that it's T infinity just refers to the fact that that's kind of theoretical. Technically, any distance from the object will be affected in an infinitesimally small way, but for the most part, you don't have to get very far before that becomes immeasurable. And then this one, so the surfaces that are surrounding an object, we refer to as T surroundings. So usually TS will mean surface temperature, SUR will mean surroundings, and infinity or the ambient. So hopefully that answers the question.
Yeah, perfect. Thanks.
Awesome. Okay. So for two-dimensional, it's actually not really that much harder than one-dimensional. It's just a matter of having a little bit more to account for. And so in this question, this one is, again, it's kind of a complicated one, but that's nice because it allows us to deal with every single situation. So we have boundary conditions at the bottom here and at the top, held at 50 degrees Celsius. That means the surface is held at 50 degrees, which means even though these nodes aren't numbered, they still exist. And you'll see, we'll just use the 50 degrees rather than a number, just makes it a little bit more simple. On this side, we have convective boundary conditions, and then down the middle, we have a very, very thin electric film that's pumping heat into it. And let's see, so we're given our Ks, 500 watt electric heater. So, so the idea with this question is that this is so thin that it's not actually, we're not going to treat this film like a conductive object. We're going to treat it like it's infinitely small. But we are going to have to incorporate the fact that there's energy being put in. So again, we'll do a similar thing where we're just going to solve a couple nodes, and then if you wanted to solve this whole equation, you would have to make an equation for all 15 nodes, and then you would have to solve the 15 equations simultaneously, which is, again, the idea. That's something that's a big pain for us to do as people, but it's actually very easy for a computer to do. So first thing we'll look at is node 1. Okay, and so this is, we're going to end up with a lot of this kind of a little bit of thought as far as when are we using delta x, when are we using delta y, and when are we using either of those divided by 2. So for node 1, we're going to say h1, and h1 referring to this one, not the node 1. So we're going to reuse this h1 in other nodes. Delta y, t infinity minus t1. And our delta y is now representative of our area. So before we would have used HA, and then our difference of temperature, but now we actually we are concerned with that direction, and so we're going to use delta y. That's something we've split up by nodes. And in this case, it is the full delta y because we're talking about this amount of area being exposed to convection. And then we're going to add K1 delta x over 2, 50 minus T1 divided by delta x. Okay, and this one's important. So again, we're thinking about, sorry, that was divided by delta y. So remember that this one is referring to the area, while this one is kind of more analogous to the thickness. So this is the node we're talking about interacting with. That's why we use the 50. So it had to travel the entire delta y in order, so that represents the thickness, kind of how far it has to go. But we're only talking about half the delta x. So it's kind of representing all of this heat flow. So half in the x direction and full in the y direction. So that's a little complicated. So I'll just power these to these next ones so you guys have them for reference. So from our node 2, and that's all equal to 0. So again, for each one, it's a little complicated. But if you just work through them direction by direction, you just go through all 4 boundaries, and you just keep track of which ones are delta x, which ones are delta x over 2. Then you'll be fine. Next one we're going to do is 7. And this one, it's all in one material, and it's all conduction on both sides. And so this is kind of our most general case. If you have something that is just being influenced by conduction all through uniform K, you'll see that it'll simple down quite nicely. So for our node 7, we have T6 minus T7. So again, because we're dealing with this one that's kind of in the middle, it's not on the edge of anything, we're going to have the full delta y and the full delta x. And so it's a little boring, but you'll see it'll lead to a nice simplification. That's T8, sorry, not T infinity. Okay. So I wouldn't have necessarily, I wouldn't expect you to follow along with that, but the idea here is all these are pretty simple. So whichever direction we're going, we're using either x or y to demonstrate our area, and the other one to demonstrate how deep we're going or the distance between the nodes. And because this is not on the edge or anything, everything is quite straightforward. And so what you'll see in the book a lot is this kind of special case. So if we have uniform heat conductivity, and we have square nodes, so only if these two things are true, this is basically saying that delta x is equal to delta y. Then what we can do is we can actually, you'll see that we can cancel all of these out, including the bottom, the top and the bottom, because delta x is equal to delta y, and get our much more simplified equation, which I didn't write out, but we can do it here. So T6 minus T7 plus T2 minus T7 plus T12 minus T7 plus T8 minus T7 equal to 0, or the other way of writing that, T6 plus T2 plus T12 plus T8 minus 4 times T7 is equal to 0, where T7 is the node that we're calculating for. And so this is something you'll see a lot, and this allows you to very rapidly kind of go through all a surface and develop a lot of equations quite quickly. And then of course another one we'll look at is we'll look at 8. Because that's right on the boundary. Okay. So we'll write a couple down and then we'll talk about how they were derived by scrolling back up to the picture. So there's quite a bit to this, obviously. We'll just finish this off. Okay, so we'll just go over a couple of these quickly. The first node, the transfer between 7 and 8, that's just a normal one. And then the transfer between 3 and 8, we add our conduction equations together. And so just to take a look at why we would do this. So between 7 and 8, that's normal. That shouldn't be a huge surprise. But to go between 8 and 3, it's actually going to be going through this part. And so we're going to have a delta x over 2 times our K2. And then the heat transfer for this side. And then same with this, delta x over 2 times our heat transfer on this side. And when we add these two up, because the delta x is the same on either side of this shape, we're just going to end up adding our k's together. So it's essentially this flux plus this flux. And so that's what we're looking at. That's what we're looking at here with the addition. And then the only other thing worth noting is our Q. So this is how much we're getting in from that strip in the middle. And of course, because we're just dealing with this node, we're multiplying it by our delta y. And that just represents this delta y that our heat is being generated. So again, for this question, at time now, we're going to be, so for this question, we're not going to solve it. We've just looked at a couple, but of course, to solve the whole thing, you have to do all 15 and stop, or sorry, and then solve all the equations simultaneously. So because it's the end of the session, I'll just stop now, ask if there's any questions. And then the next one is pretty quick. So I'm just going to continue on because these are recorded anyway. And then if you can't stay, then you can just watch the video on the website after. So any questions right now?
Yes. Why for some cases we have delta x over 2?
Yeah. So yeah, I've been trying to explain it throughout, but I can do a quick summary. So I think this visual, I think part of it, you need to work through them and try to make sense of it yourself. That's kind of what I did in preparation for this. Because you just have to think about each case. So again, this was node 1 that we started with. And so when we're looking at the convective heat exchange that goes this way, and if you think about the fact that we've drawn our element within, so I'm going to erase this for a second and redraw them just for our own reference. So we've taken our element and we've drawn it. So this element here is this shape. Maybe that'll help seeing it on this diagram. And so the element, the part of the element that actually is within our conduction domain here is delta x over 2. This dimension is the full delta y, and then this dimension is the delta x over 2. And so the idea is to where the convection interacts with this, we can see that it's the full y dimension, because that's representing area. Then when we get into the conduction, we have these two things. So I've drawn these arrows, but I never wrote. This is defining the area that it's interacting with. And this one is defining the distance, I guess we'll say. And that comes from the fact that our original conduction equation was Q dot is equal to K delta T. Or minus K delta T. Sorry, Ka over L delta T, where the area kind of referred to this part, and the length referred to the depth. So when you're constructing these equations, you just have to think about the one on the bottom is referring to kind of how far it has to go, and the one on the front is talking about how big of a distance you're talking about. So for the case of the way this one, so this one's talking about this node interacting with this. So the area that it's interacting with is this x over 2, because we're talking about this direction. But then the distance it actually has to go is the full y.
Okay, perfect.
Does that make sense? Yeah.
Yes.
Excuse me, sir.
Yeah.
If one side is insulated, how are we going to treat that node?
That's a good question. Actually, so I'll just do the next question. And again, I know you guys only necessarily have these 45 minutes free, so feel free to leave and then you can watch the video after. But I'll do the next question just because it has some helpful stuff for symmetry and for insulation, and it's not a very long question. So that'll hopefully this will answer your question. Okay, so this is consider two-dimensional heat transfer in these two long solid bars. So this is one of them and this is the other. We're only going to do this one just for time. So they have these measured temperatures. So on all of these edges, we know all of the nodes. The thermal conductivity is K is equal to 20. No heat generation, so that's nice. Using the finite difference method with the mesh size x equals y as 1 centimeter, determine the temperatures of the indicated points. So this one is kind of a tricky one because what we're going to do is we're going to, I guess it's just very elegant. So we're going to make all these kind of symmetry assumptions, and then we're going to end up with much less equations than we may otherwise would. So the first thing to know is for insulation. So I'll just draw, actually, even for one dimensional, it's the same. So let's say this is node 1 and this is node 0, and this is insulated. And then this is node 3. Sorry, we don't need this node 3. So what we're going to say about this node 0, because it's insulated, you can think of, intuitively it would make sense if this was hot. This would get much hotter than it would if it had somewhere to go. Because it's insulated, it means heat can't escape, also can't enter. So the way it works mathematically, and I think the proof is in the book, you just assume symmetry. And so you essentially say that the heat conduction, so not super clear. So we have a shape here, we have insulation here, and we're gonna basically say this insulation is equivalent to also having this temperature node there. And so the temperature that we would measure would be as though the temperature is coming from both sides. So K T1 minus T0 over this distance, which would be delta x, plus, and then on this side it would be the same. K T1 minus T0 over delta x. And that's all equal to 0. So we'll do an example, but this is basically the idea is here that you can essentially double the effect of this, because this would then be 2K T1 minus. And again, this isn't a proof or anything, this is more how you do it. But again, it does make sense. If you're heating this up, this was going to get hotter than if, again, the heat had somewhere to escape to. So hopefully that makes some intuitive sense. So what we're going to do is, so we know that for this case, because it's two-dimensional, it's actually going to be as though it also has a node 2 here, and it also has a 250 boundary condition here. That makes sense. Okay.
Excuse me, sir.
Yeah.
For the drawing on bottom,
Yeah.
if we cancellate the k and delta x, so we get T1, 2T1 minus 2T0 equal to 0. So T1 equals to T0.
Oh, very good point. Yeah. Yeah. 2 and then T1 minus T0. Yeah. And again, that would have to be in this case where we have uniform K for the solid we're dealing with, and also uniform node distances. But by the way, I wrote these, it would assume that because I have no K1 or K2. So you're right, then get simplified down further.
Okay, so they have the same temperature, node 1 and node 0. Right?
Yes.
Oh, I thought 0 should be hotter, but they're the same. Okay. Thank you.
Yeah, okay, that makes sense. And actually, this idea of insulation isn't introduced until two-dimensional in the textbook. I wonder if that's why. Yeah, because in one-dimensional, I guess it kind of gets boring. But I think that's been true in our past examples as well. If you have some sort of solid And sorry, that's not a good example. But if you have some sort of solid, you have some sort of heat flux, and you have insulation, then your whole wall would be at steady state would be at the same temperature, because once you've kind of heated up to a point that has reached steady state, I guess then the heat has nowhere to go. So maybe this isn't a great example, but that is a good observation.
Yeah, that's true. Thank you.
Yeah, that's interesting. So okay, but so that fact doesn't exist here because we do have this two-dimensional heat transfer, so it's not as constrained. It can kind of come here and come out. Okay, and so that's the first simplification we're going to make, is that we have kind of symmetry across here. And then the other simplification we're going to make is we're going to have symmetry along the middle. And so we know that 2 is equal to 3, 4 is equal to 5, and we know that because all of these temperatures match up. If they didn't, then we would have a different situation. We also have a couple other nice things. So we have uniform K, and we have our delta x equals delta y, which means we have our square boundary conditions, which is kind of exactly what we want to write that super simplified equation. So we're going to start with node 1. So again, we're going to kind of go in every direction, and it's going to be this temperature plus this temperature plus this temperature plus this temperature minus 4 times this temperature is equal to 0. And that was the equation we derived previously. This one. The temperature in all 4 directions, 4 times this one, 4 times the node you're talking about, all that's equal to 0. So for node 1, we have 150 plus 150 plus 2 times T2. And this is a trick because we are assuming T2 and T3 are the same because it's symmetry down the middle, minus 4 times the node we're talking about. So 4 times T1. All that's equal to 0. Our node 2 is this one, so we're 200 plus T1 plus T5 plus T4, so all directions, minus 4 times the node we're talking about is equal to 0. For our node 4, so this time we're going to have 250 from up there and then 250 from our symmetry across the installation. And then also our node 2 and our node 2. So again, one because it's there and the other one because it's symmetrical across the installation. Minus 4 times 4 is equal to 0. And then for our node 5, actually, this is going to happen, what you pointed out. So this time we have our T2, and then our 3 is also a 2, and then we also have our 2 here because it's symmetry across the insulation, and we have our 3 here, which is also equal to T2, and so we're actually going to end up with 4 times T2 minus 4 times T5 is equal to 0, which, yes, means that T2 is equal to T5. So I think that is the exact same situation you were pointing out. Because we're symmetrical here, it just has nowhere to go. So at steady state, all the heat will balance out. Okay, and then this is actually something that's fairly simple to solve. So I think it's a good example just because simplify is so easy. I could see this being a test question. So I shouldn't speculate too much on the test questions because again, I never took this course. But this turns from all the other questions were quite a few nodes, quite a lot of simplification work required. This one would be fairly reasonable to solve. And I won't go through all the analytics, but I think you guys know how to solve 4 equations and 4 unknowns at this point, especially when one of them is this easy. And T5 is equal to 2.